How do you video?
Yeah. Then can you send it to me once you have it? Nice. No? I know they'll just copy it. Just the ground the office. I have no idea if this is
Where are they? Oh my God. Okay. What's the time? Oh, civil. Okay. All right. Unless you don't turn to them if you don't answer a question. Ask them for the all over. Okay, welcome everybody. My name is Tom Peter. I'm chairing this procedure here and just overlooking that everything is going according to the rules. Let me, first of all, of course, welcome the candidate here. So, Ryan, we are very much looking forward to your presentation, and then introduce the committee. This is Dr. Justin Sheffield from Southampton. He's our independent, and he's actually here on a vacation activity because officially he's on strike. So we are not supposed to say that he's working, right? No, on a more serious note, we are extremely happy to get external photographers here because we know how much work it is and how much time it needs. So thank you very much. Then we have two other committee members. That is Lukas Gudmundsson here from the Institute, who you all know, and the Dr. Mother, Sonja Silvia. And this said, the floor is yours. You know the rules of the game, roughly 20 minutes, and then we go into questions first by the committee. And then after that, you are all invited to ask about water availability in a warming world, which you all should be interested in.
Thanks a lot, Tom. So, yeah, good afternoon and welcome also everyone from my side. And as Tom just said, I would like to talk to you today about water availability in a warming world. So water availability has direct impacts for people around the world. In the figures here, you can see the Mekong River in Southeast Asia at its lowest level in the last 100 years. You can also see an inundated crop field in Argentina. So both of these events have consequences for food security, for example. But other aspects are also affected. For example, there was several high economic losses during last year's drought due to reduced cargo ship capacity in the Rhine. For example, and last but not least, ecosystems are also affected. So as illustrated in this last figure, the drying up of rivers in Paraguay led to a widespread death of caimans and capybaras. So, and after the short introduction, now I would like to start to define water availability by looking at this very simple schematic of the exchange of water fluxes at the surface. At the surface, we have an income of water through precipitation, which then transforms into surface runoff or runoff of groundwater runoff. Or in the other hand, it could also be evaporated or transpired back to the atmosphere through vegetation. Now, if you take the difference between this input and the output of these fluxes at the surface, we have the surface water balance, which indicates that precipitation minus evapotranspiration minus runoff will be equivalent to any changes in storage we have in the soil. Now, the sum of both surface runoff and groundwater runoff plus the changes in storage is what is typically defined as renewable freshwater resources. And therefore, we also consider this definition here to define water availability for the thesis. So, sum of runoff plus changes in storage, which will also be equivalent to precipitation minus evapotranspiration. One last point is that evapotranspiration does not only play a crucial role for the water cycle, but is also directly linked to the carbon and energy cycles of the climate system. Now, after this brief introduction, a brief overview, I would like to state the overarching questions I address in the thesis. So first, what factors influence water availability on land? And for this, I conducted two studies. And the first one, we looked at trying to clarify the controls of long-term annual mean partition of precipitation into evapotranspiration and runoff. And a second study where we focus on providing an overview of nocturnal water fluxes. Then the second main question we try to address in the thesis is, how does water availability change with global warming? So for this case, we also conducted two studies. And the first one, we looked at observed changes in water availability since the beginning of the 20th century, focusing on the dry season. And on the second study, we looked at future projections of water availability, and then tried to constrain the uncertainty. So now, after this brief outline, let me guide you through the results of these four different studies. And let's start with the first one, where we look at the controls of the long-term partitioning of precipitation into evapotranspiration and runoff. So this is commonly analyzed in the literature through the Budico framework. This framework defines the ratio of evapotranspiration over precipitation in terms of two variables. On on the one hand, in terms of the long-term ratio of potential evapotranspiration over precipitation, and on the other hand, a single parameter omega, which will include or integrate the effect of all additional possible controls. As illustrated in this figure, long-term evapotranspiration cannot exceed potential evapotranspiration, and can also not exceed long-term precipitation. So all solutions to the Bulico framework will lie in this space. And here we see also that as the long-term potential evapotranspiration over precipitation increases, or as omega values increase, these two cases will lead to an increase in the overall ratio of evapotranspiration over precipitation, and therefore favor ET over runoff. So the Bulico framework, and given by this equation here, was introduced to the global scientific community in 2004 by Slang. So our approach here was to conduct a systematic literature review of all studies, citing this paper here that introduced this equation. So I did this by going Web of Science and looking at 1, 2, 3, 4, up to 170 studies. I went through most of them, found like if they had data on tables, screened them, extracted data out of tables, and in this way we were able to compile a new data set. So we have a newly assembled data set of long-term hydroclimatological measurements focused on the omega parameter of the Bulico framework. So this is shown by this map here. This is the data we managed to assemble together, and it corresponds to information from 1,900 catchments around the world. Now, as I said at the beginning of the study, our focus here was to try to analyze the controls of the long-term partition of precipitation into evapotranspiration and runoff. So to do this, we found also from the literature review 26 different indices that have been proposed in the literature as relevant controls of this partition. Here classified in climate-related features and landscape-related features, and computed partial correlations with the omega parameter. So how you should read this plot is that if you have red colors, that will indicate that there's a positive correlation between the given index and omega, indicating that an increase, for example, in mean annual temperature corresponds to an increase in omega, and therefore will favor evapotranspiration over runoff. The other way around for blue colors. The first result we can see is that from all these indices that have been proposed, most of them are not significant, which is denoted by the X marks here, with the exception of snow climate types. The second result we see is that climate and slope controls appear to be much more dominant than other landscape controls. A third point I want to make is that, of course, the controls will vary according to climate type. We have, for example, for controller climates, topographic controls playing a higher role. In arid climates, the number of rainy days in a year being relevant. And warm temperate climate types, you have the timing of precipitation and potential evapotranspiration as a more dominant control. And in snow climate types, the fraction of precipitation that falls as snow plays a very important role. Lastly, we see that vegetation-related indices appear to play only a minor role. And this came as a bit of a surprise, given that in the literature, this is often considered to be a very relevant control for the partition of precipitation. So with this, I would like to finish up this first result for the first study. And now we'll move to the second study, where I analyze nocturnal water fluxes from observations and also from climate models. So these are typically overlooked fluxes in the literature, especially in the hydrological and climatological community. And before I start, here I will be showing you results of a nocturnal water loss, which is defined as nighttime evapotranspiration minus condensation that might occur. And most of the results I will be showing you are for nocturnal water loss relative to total evapotranspiration. And now let's start from the observational results. Here we used information from the FluxNet sites with daily covariance measurements. So I processed data from 99 sites that included 3 or more years of data shown in the map. And as a rough number, you can get already from observations, nocturnal water loss is approximately 6.3% of total evapotranspiration across all sites. But we can also look at the distribution of the sites given here, and then we see that there are quite a few sites, for example, where these losses can surpass 100 millimeters in a year. It's quite a lot. But on the other hand, there's also other sites where instead of having a loss, we actually have a net gain due to condensation during the night. The corresponding values, if you look at the fraction, are, for example, the 5th percentile of the distribution is 1% of total ET, and the 95th percentile would be 15% of total evapotranspiration. Now, this was for the observational data. But what was also interesting was to look at nocturnal water losses in climate models. So here I show a map of the multi-model mean for the nocturnal water loss from 26 different CMIP5 models. And some of the features we can see is that overall, the global average agrees relatively well with observations. We have a global average of approximately 8%. These values are similar, for example, in regions like Europe, North America, Europe, China, and India, values of 9%, but we have some regions with a bit higher values. For example, the Mediterranean and Australia can reach up to 13%. In the equatorial belt, values seem to be a little bit lower when looking at the relative value, but if we look at absolute magnitude, we see that in most of these regions, we also have nocturnal water loss surpassing more than 60 millimeters in a year. Now, these were results for the multi-model mean, but it's also interesting to look at the spread of the models. So how different are the models? So here I showed two maps, one of the 95th percentile and one of the 5th percentile of the model ensemble. And here we can see already those quite striking differences. For example, there are some models that suggest almost everywhere in the world nocturnal water loss of more than 15% of total evapotranspiration, which would be quite significant. Whereas other models suggest quite low values and even a net gain in parts of the tropics and higher latitudes. So this very strong disagreement across models is also important because, for example, it can explain already a substantial part of the disagreement in total evapotranspiration across models. So with this now, I would like to finish the part of nocturnal water loss and move to the second part of the thesis and address the question of how does water availability change with global warming. So let's start now with the observed changes with global warming, focusing on the dry season since the beginning of the 1900s. For this, I use two observation-based reconstructions for runoff and fluctuations in terrestrial water storage. This will correspond to a definition of water availability, so also correspond to precipitation minus evapotranspiration. As I said, we will be looking at the dry season, which I here define as a month with minimum precipitation minus evapotranspiration. And we analyze a change, as I said, from a recent period relative to a period in the beginning of the 20th century, so 1902 to 1950. Now, what does the data show? So the data shows an overall predominant drying of the driest month of the season, 56% of the land area, and with some patterns that start to emerge. For example, in regions like North America, Europe, and Australia, 3 out of every 4 grid cells show that there's been a drying of the driest month. Now, if we look at the magnitude of the drying in these regions, it can be up to 23% relative to the water availability that was there at the beginning of the 20th century. These are results for the single driest month, but if you look at the driest 3-month period, for example, results are also largely consistent. Now that I've showed you that there's been an intensification of the dry season, the question is it related to decreases in precipitation, or is it related to increases in evapotranspiration? So this is shown by these two maps here. We have the contribution of precipitation and the contribution of evapotranspiration. All grid cells in red indicate that either variable has contributed to the intensification of the dry season. So I think you will all agree with me that it's quite clear that it appears to be dominated by evapotranspiration, particularly in exotropical latitudes. And lastly, the question was, okay, we have an observed intensification of the dry season, but how is this related to the global warming we've experienced since the beginning of the 20th century, about approximately 1 degree already? So for this, we had the null hypothesis that the observational pattern is not any different than what we can expect from climate variability. And to test this, we assume that climate variability is given by thousands of simulations of models forced with pre-industrial conditions, which do not include greenhouse gases. We use all these simulations and correlate them to the multi-model mean from the historical period, which does include greenhouse gases, and obtain the following distribution. Now, if we do the same correlation but with the observed pattern, we see that it lies at the very far end of the distribution. So therefore, we can safely reject our null hypothesis and say that observations or the observed pattern is not really expected from natural climate variability, and thus conclude that it has been an extremely likely contribution of human-induced emissions to the intensification of the dry season. Now, with that, I would like to move to the final study where we looked at future projections of water availability. So that was the previous study was observed changes. Now let's look into the future. So this is focusing on changes in multi-decadal mean not of the dry season anymore. And we will look at changes from a period at the end of the century with respect to a period pretty much at the end of the 20th century. This is an example where every line corresponds to an individual model, just to illustrate the uncertainty in the future projections. We have, for example, for this region, some models suggesting almost 200 millimeters of a wetter future, whereas other models indicated that it will get drier in North America by up to 100 millimeters. So how we try to constrain this uncertainty, we find, first of all, a relation between the present wetness state in the model and the future projections. So this is given by this map that indicates the correlation at the grid cell level between long-term mean annual precipitation in the present day and the future change projected with the models. So there are some regions, for example, here in the Mediterranean and Southern Africa, where you have a negative correlation, which will indicate that models that are wetter in the present can dry up more in the future, because models that are already drier in the present can only dry it as much as the little water they had to start with. But on the other hand, you have also regions with positive correlations. In these cases, it will indicate that models that are wetter in the present will become even wetter in the future. This is probably related to the persistence of biases in some of the models and the intensification of the hydrological cycle. So now, overall, from this relation, we can conclude that we can make use of the models that agree best with observations in the present day to put more trust in their projections of future changes in water availability. So here we use the Markov-Chain Monte Carlo approach and computed for each of the 36 models in CIMIC 5 its probability of being included in the constraint ensemble that will agree best with observed precipitation. I think it's quite striking to see that many of the models, if included in the ensemble, they don't really improve the agreement with the observation distribution. So then, from this step, what we did is use these probabilities and computed and created a new constraint weighted ensemble instead of the normal CIMIC 5 ensemble where all models will have the same weight. So now let's go into the results, comparing the full ensemble, our previous state of knowledge, and now our constraint ensemble, which has hopefully better projections of water availability. So now if we look at the differences between the two maps, you can see, for example, that the constraint ensemble shows on the mean a little bit of a wetter state across most of the northern latitudes, but also other regions, for example, like a higher drier future for the Amazon is projected. Now this was result for the mean, but then here is also interesting to look at the spread, what I showed you in the beginning. So here in red is the full spread of the full ensemble, and in blue the spread of the constraint ensemble. Even though the mean didn't change much in this region, the uncertainty is much smaller. Another way to analyze the differences in the extremes will be of thinking of a probability ratio. So actually this map is not the maximum and the minimum, but the 5th and 95th percentile, which will mean that you have a 5% likelihood of exceeding these extreme changes in water availability in the full ensemble. If we now look at the constraint ensemble, the likelihood is much, much smaller than 5%. So if we compute this as a ratio, this will be shown now in the text maps. So this is for the case of extreme drying. The probability ratio is 1/5, so indicating that it's almost 5 times less likely that you will have extreme drying as indicated by the full ensemble, for example, in regions of West North America, Europe, and Southern Africa. This reduction in extreme drying is found in 73% of them, and similar result is found for extreme wetting. So now you also find quite a strong reduction of the extreme wetting given by the 95th percentile of the full ensemble. So with this now, I would like to finally wrap up everything again. I know it was kind of fast, there's a lot of material. Let's try to summarize it again, everything in the final slide. So the two questions we wanted to address on the thesis was what factors influence water availability on land. So the first study, as I showed you, we provide a summary of the controls after a comprehensive assessment of previous suggested controls in the literature through a systematic literature review. Results for this study can be, for example, important for model evaluation and development, seeing if the relations we found are actually present in models or not. The second study, we looked at nocturnal water fluxes. I think I showed you that it can be quite relevant in observations and models. And another important point that I already mentioned is that the strong disagreement between models can be something really to do further research on. It could explain part of the differences already in total evapotranspiration across models, and especially also looking into the future, they explain a large part of the future change in evapotranspiration. And lastly, the second question that I addressed was how does water availability change with global warming? And then I showed you first results for changes since the beginning of the 20th century, where there was an observed human-induced dry season intensification, which was driven mainly by increased evapotranspiration rather than decreased precipitation. And in the last study, we used an observational constraint on observed precipitation to show that there's a reduced likelihood of the extreme projected drying and wetting tendencies from the full simplified model ensemble. So I think overall with the thesis, I try to contribute to advance our understanding of present and future water availability. And I hope you agreed with me, and if not, please ask as many questions as you have. Thank you.
Thank you, Ryan, for a very clear and lively presentation, which we are now going to drill the holes into. But who wants to start?
I think I get the pleasure of starting. Thank you very much for the presentation. It's all very interesting, the thesis overall. But I do have a few questions. Perfect. I'm not going to ask them all, but I'll give you this document afterwards. So my first question is a bit general. It's thinking about the motivation for the given work. So you showed some examples right at the beginning of specific places where there were issues with too much water, too little water, and different sectors that were being impacted. I just want to know from your kind of maybe a bit more of a personal point of view what the motivation was for looking at this subject and doing this particular set of research.
It could be a very long story. I'll try to keep it simple. So actually, a civil engineer is a background. From there, I didn't know what I wanted to do. I did my bachelor thesis in psychology. I spent almost 3 months doing field work in time regions in the mountains, pretty much where we get all the water from for a city where I live in Ecuador. So that's how I found out my life goal and research, let's say, at that stage, or a bit later on. Then I moved here, just doing the master thesis also with Lucas and Sonia. I started to become much more interested also in the scientific problem, not only the human-related topic, and then I think it's something that it impacts so many things, right? So not only water, but as I said, it's related to food security, it's related to streams, a lot of the work that we're doing here, to the coupling with the energy cycle. Now it's also related to links to how much global warming we will have, how much more carbon emissions, how much we can capture if there's droughts. It's going to change from a carbon sink to a carbon source to land. So I think twofold maybe to sum up, very scientifically interested and also very personally interested in water availability, since we get most of the water also from the mountains in the city where I come from.
So how do you kind of connect back to your original motivation of being an engineer, I guess, trying to solve practical problems? Or do you try and make this full circle and come back to this is more of a higher level research analysis.
Yeah.
Are you motivated to come back to where you started almost?
Partly yes, and at one point I also detoured a little bit after talking to Lucas. So he also changed a bit of my mindset. I was usually stuck in small catchment analysis, and then it's like, okay, but that's only useful there. You want to be useful to the world. So then I also moved to the large scale hydrology.
I can argue the other way.
Yeah, on the end, I also agree. On the other hand, if you want to really have local impact, these studies are probably not necessarily what you will do in the end. You have to again come back and conduct research at the case specific level. But I think it could be useful. A lot of the results we have for policy, European level, continental level, country level discussions of policy, for example.
Sure. Okay. You talked a lot about the observational data and the reasons for using the data sets that you did. You didn't really talk about the problems with the observational data. Maybe it's obvious, I'm not sure. Can you talk a little bit about, if you tried to do any of this large scale analysis with observational program data, what would you get?
That's why it took me 3 years. Otherwise, it would be very simple, especially for the first study. Then I really also had, again, quite a strong impression when I was doing the literature review. Looking at most of the studies were studies that provided information from catchment, and you have 2 or 3 stations of precipitation, ground data, and then you get an estimate of long-term precipitation for a catchment of 5,000 square kilometers. okay, you start to think, I already was a bit aware of these problems, but just interpolation, you have data scarcity. A couple of the maps I showed, maybe it was a bit too fast, but you usually see most of the observations concentrated still in North America, Europe, still quite a lot of regions where you have much more uncertainty. I also didn't really talk about that, but for example, for same case for the reconstructions, a lot of the model skill, comparing with observations, we see that regions like South America, Africa, there's still much more uncertainty. I don't know if that already answers part of your question, but yeah, of course, there's interpolation, spatial coverage. Now we have satellites, a bit of remote sensing, we get better spatial coverage, but it's also shorter term. So then I think the work of Vincent and Jonathan with Lucas for the reconstructions that I was able to use for the first study is quite valuable. But of course, there's still a lot of uncertainty there. We don't really have too many other products to compare them to. Now there's some new simulations coming out, so we can still use a bit model portion of analysis. And then, of course, I've tried to read your work. I know like all the work you've done, the colleague you've done with like observed precipitation data sets. I think it's probably the way to go still. Like that's one of the main conclusions in the thesis. I think that if I would have money, I would put probably more money still on better observing at higher resolution precipitation and evapotranspiration than probably doing much more work on model development.
But if you didn't have any money to go out and measure a bunch of stuff in the Congo or the Amazon, where you see some of the biggest changes and some of the biggest uncertainties, what could you do to constrain those data sets better?
So part of remote sensing, you have some information based on that. Say then there's, I don't know how good is it going. You can think of probably there's still governmental level data in some of these countries. I think it's also a big problem sharing the data. There's also like a lot of the efforts in terms of just digitalizing data. I don't know how much you actually have there, but it could be useful. I know, for example, for Ecuador, we do have data going back to the 1900s, but you need to talk to 100 people. It's tons of bureaucratic. Nobody knows where it is, and you find it in the basement or somewhere. So then I think that could be one option to go. And then, of course, you can try to think about conceptually, think of the things you can measure or integrated characteristics. I think in that case, measuring runoff is usually the way to go in the hydrological cycle. Or we integrate a lot of information from the field catchment. That one station.
Okay. I was a bit, I don't know the word, concerned, maybe not concerned, with your research questions, which I didn't see were linked to research gaps, especially in the introduction. Maybe it was a little bit more in the actual research chapters themselves. So I'm wondering, could you kind of summarize where the real research gaps are? So maybe obviously in nocturnal water loss, not much has been done in that.
Yeah.
In terms of the other ones, what are the key kind of research gaps
So,
that kind of motivated those research questions?
the idea for the first study was that, of course, it was a hot topic back then. I think it's still is. I'll show you that there was 70 studies citing the study of song that introduced the political payment. I think I checked it yesterday, it was up to 340 already. It's doubled in the last 3 years. So that's been something that there's lots of literature on, and there was a big kind of a debate there. A lot of papers being produced. There was disagreement, for example, in the role of vegetation. One of the things we decided to have a bit more of an observational assessment of these indices that have been suggested. There was a paper of Chris Williams that was saying that, for example, less forested catchments were favoring evapotranspiration, whereas the actual paper from Sung had some catchments in Australia where he was saying actually more forested catchments are favoring more evapotranspiration than normal. So I think in that case was more of a scientific debate that was going on at the time, and we tried to summarize with the literature review and provide as strong observational evidence as we could of the actual constraint. And then I think in the terms of the dry season intensification, a bit more of a detection attribution study, I think that's also quite relevant. So the latest IPCC, at least AR5 now before AR6 comes out, had all these statements claiming that okay, we have low confidence or not enough confidence on observed changes in the water cycle. I think it's clear that we can attribute increases in temperature, for example, to human-induced emissions, but the water cycle really changes due to, of course, we have ENSO, we have PDO, we have a lot of other variability affecting internal family variability affecting masking the signal. So then I think now it was the time, especially using the observed based reconstructions, it was a unique opportunity to look at this. And for the fourth one, also the motivation, as I said, the spread of the full model ensemble, it just doesn't give you much to work in terms of what resources done in an adaptation. So we tried to find a physically meaningful way to constrain this. I think it would be also quite interesting to look at that now. For example, it's a constraint holds for the six model.
So one comment you made about the vegetation for the first research chapter, where you found it wasn't much in control despite there being some evidence from individual studies that it was. What do you think you didn't see? Because what I got out of that chapter was where there were some equine climate controls and things like catchment properties as well. But the ones you were expecting as well, for example, vegetation and perhaps the human impact. You didn't really discuss why. You didn't say you thought because of this or.
Well, I think the paper was already quite long. So, but yeah, like I think there's of course a lot of things probably just climate related signals, especially if you look at a bit of a larger scale, they're much more likely to be captured. I would say maybe it's a smaller effect of vegetation playing involving a catchment. For the study, we also look at different catchment sizes divided in our sample. So we still didn't see any change there. Of course, there are lots of other issues that could have been different. Right? So, I said, presbyterianism, that's humanity inside the catchment. We're also testing the correlation catchment level values of omega with information from other data sets that are graded products. So then, how much do we trust the location, the latitude, longitude? Oh, I think I have one slide on there that could help illustrate that problem. More or less this. So we're combining this type of information, right? So it depends on the size of the catchment first. If you actually have matching information of the control that we're correlating with the observed values of omega, we can have catchments that are much bigger than the grid cell we can data from. We have, in other cases, several catchments inside only one grid cell. So that's why I would think that overall we see a higher signal of climate because it's much more homogeneous. And that's scale. Okay. So that could be one.
So in terms of those kind of inconsistencies, those regional controls that are just for that region, which was the kind of problems you kind of identified in those individual studies. Do you think you've reconciled those things now, or there's still some open questions, perhaps, for example, with vegetation, maybe other things?
I think it's still a bit of an open question, but it's probably useful to see, especially if you want to keep doing this research at large scale, to don't fall down this rabbit hole, for example, and give at least the same number of priority to the different controls. Because what I felt was at one point when I was reading most of the studies, I felt like 50% of them were looking at vegetation as an important index as their hypothesis and then just test that. And probably one study looking at or maybe I'm exaggerating a little bit more, but of course, much less of a proportion looking at, for example, the timing of precipitation and potential water creation. So I think in terms of this, like our study was trying to put all these things a bit more into context and say, okay, if you want to do research, at least this appears to be a bit more important. Also pay as much attention in the literature to this, and not only focus on.
So just following up on that, so you mentioned about these, there were some studies that were looking at attribution of changes. Yeah, so climate change, land use change, things like that. Yeah, so you're saying that you need to be aware of the other controls that may be giving you a false kind of signal. Yeah. If you're just looking at one of these variables that you're hypothesizing about, how would you do it? How would you use this framework to attribute change? Is it possible to use that if you throw in all these factors that you think are important?
It's quite tough, so we don't do that particularly in our study, but that's true. A lot of studies from Google actually divided their data period record into two, and then look at the temporal changes actually, and seeing how much will change there. A lot of the indices I showed, of course, will be much different across catchments. If you're focusing on the same catchment, for example, slope, which plays a catchment slope, which plays a quite relevant role, not really going to change unless you really go and change dramatically the landscape and start exploding a mine there. You won't really change that. But I would consider that, yeah, there's also this one paper from both I think they're trying to reconcile if you could actually apply the same framework to spatial differences and temporal differences. Then, of course, there are also other things to consider there. I wouldn't be so optimistic of using it to attributing change, especially in the way that it has been done in many of these studies. So many of these studies that try to attribute human-induced change directly by looking at the disentangling contribution of the long-term climate change for the potentially transpiration or precipitation ratio. and saying that omega is everything else that's human related. I think one of the main things we showed in this study was that omega is not only human contribution directly. We have a lot of other climate related indices that are also included there.
Okay. Just on the second research chapter on nocturnal water loss, just briefly, what was the motivation for looking at that? Because it's a novel study, it's interesting, but so where did it come from?
So that's a bit out of my side. So yeah, I guess Sonia wasn't, I don't know, maybe you can contradict me. I think Sonia wasn't so happy about it in the beginning.
Okay, I like it.
If I detoured on that one. I think partly again, I actually was expecting a bit more on the other end of the results when I started. So also I've done a bit of the work that with Dominic installing isometers. We have similar network in Europe and in Switzerland during the PhD. And usually when we install, I went the next day sometimes, and now it's not substantial like dew. Actually, didn't rain. I see a lot of dew. So my guess or my assumption was that we were actually miscapturing a lot of the input of water into the system. Then I started reading about, looking at plasma data, and covariance data, and it appears that it was completely off, but it's still interesting. So my main motivation was to prove that dew was very important. That apparently nighttime evapotranspiration is higher.
That's a good story. Coming from some observations and then finding out it's different from what you expected. Yeah, it's a good story. So in the end, there were some thinking about the controls on nighttime evaporation, and you also compared with the models as well, didn't you? So there were some obvious things that were controlling this, but also some less obvious ones, I think.
This doesn't have the whole version of the paper, but
right. So a bunch of obvious ones like the available water and the climate controls, but also some other things that you can really measure or understand too well. Is that correct? So I'm just trying to. In the end, you didn't actually say too much about why you see these biases in the model. It was a comparison of the observational data and the models, but no.
So we have.
I was missing the kind of physical understanding of why the models were.
Yeah, that was actually one of the main points from the reviewer team, or one of the reviewers. I would love to do that study. I hope there's more runs now. But like the runs we had to use higher time resolution output to be able to divide day and night. So the actual information we had to be able to just take nocturnal values from the models was only, for example, temperature. We didn't really have like wind speed during night and the models of output already or BTD or anything. But with temperature, we already see, for example, that there's quite a strong correlation. So models that have higher temperatures during the night are the models that are actually on the higher end of nocturnal water levels. So this is around like 45% of them have a correlation higher than 25. So that's like one point that we can start to go in.
In some ways, temperature is a state variable.
Yeah, it's not really a result. Yeah, I will still argue that it's partly related, especially to drive the evaporation, not necessarily transpiration. But if you have higher temperatures and higher in the model, you will still drive higher internal evaporation. But on the other hand, yeah, it would be really nice to look into the actually, if you can really try to say, take apart the model and say, okay, what parameter is different in what model, or
what's your guess in general? Because the models are generally too high, aren't they? Are they too high?
There's a huge spread. So on average, they're roughly the same as the observations.
Okay.
To balance it out, but because we have some models that are extremely high, there were some models for the 40th percentile, well, for the 95th percentile of the ensemble that was showing almost 40% of total evapotranspiration happening during the night. My assumption there, that's probably even a little bit of tuning, or they're not really looking into higher time resolution fluxes.
Sure. Fixing some other problems.
Yeah. I think it's a very interesting question to still go in deeper into it. There's like I got comments from a few of the reviewers, more from the plant physiology community. I think there's a lot of suggestions there. Also, like why wouldn't we have nocturnal water loss, or not even water loss, but we have sap flow in the trees. And then there's the argument of we have to avoid embolisms, to hydraulic redistribution of the water for the plants. But on the other hand, you think there's no associated carbon gains. At least that's a hypothesis now. So So I think that's still quite an open question, and that's how we try to frame it in the paper. So future research on this area.
It's the easy route now.
Yeah. Well, I can do part of the research if I get money.
Okay, so the third research paper that was drying of the driest part of the season. So I had a few specific questions about, for example, the reference period. Why did you choose those reference periods, which seem a little bit odd because they were different time lengths and potentially you don't have many observational constraints in the earlier period and you have lots in the
We
later.
ran a lot of sensitivity tests. I tried different periods, see if the results didn't change too much. One of the main reasons we also avoided the 1970s to 1980s a little bit was also the aerosol effect on the results there. We have a strong aerosol signal there. And it's probably not too representative of what we wanted to show. Right. But even then, I think in supporting information, I show sensitivity tests for taking different periods, taking 30 years in both cases. The results are still overall mostly consistent, especially for the pattern of higher latitudes, African corn in Australia. Most of the other parts, I would say, that's still quite uncertain.
Did you calculate any statistics on that sensitivity? Because I looked at those maps, and even with my own eyes, they looked like there was some sensitivity.
Yeah, there is definitely, especially that's why, especially at.
So I wasn't convinced that there wasn't an issue with the time period. Maybe you did calculate some statistics.
This case we have, considering beginning of the 20th century, now not a full 25 years. Well, I guess I don't have the actual map here. So they try to compare. Right. But I think overall, like the patterns, as I said, most of North America, Europe, Southern South America, the African Horn, and Australia, you see it pretty much most of them. I guess this could be like this one. I would say is actually more related to where we decided that we probably want to avoid a bit part of the aerosol effect. But of course, there's going to be also some estimate of the signal we have. As I said before, just natural thermal variability. Depending on the period you will take, you'll have more La Nina events. I think a lot of other effects with different.
Well, just as a general point, when you eyeball results like this,
it's probably
probably needs a bit more in-depth analysis to actually show yes, quantitative reasons are the same.
Yeah.
Or good reasons for not choosing a period.
I think it's a good point. Yeah.
Okay. A little bit more on this chapter. So that you basically said that ET was driving these changes.
Fuel cell under construction,
which is temperature driven.
You would assume so, yes.
You would assume so.
Yeah.
You didn't really look into that apart from deducing that from climate model simulations. I mean, could it be other things? Could other things confound it? I mean, there's lots of evidence.
Could definitely
contribution building about changes in radiation.
Yeah, and definitely contribution of a lot of the other changes, right? That changes in radiation. We have also global warming, global dimming. Towards the end of the 20th century, we have these two periods there, more in shorter time scales, I think. That's why we also try to take a little bit of a longer period to avoid this time variability. So it's 30 year, and that's why I also took 50-year period in the beginning of the 20th century. To avoid that.
But if temperature is going up to increase ET, should be going up as well globally with temperature?
Globally, yes. So that's the other thing. The thing is for the dry season. So if you look at the actual maps of annual changes in precipitation minus ET, I think I also have a map here. I can go back if you want, but then the pattern is not there. The pattern is not clear. So this is pretty much by default and by definition, it's more related to the months with driest or months with minimum precipitation minus local concentration. And therefore, just through precipitation variability throughout the year, you're likely to have some months where you have very low precipitation. And then just variable, it's also not really bounded there and can really go up, it will be local concentration. I think there's, I don't know if it's out already, but there was one study from people in the US that at least they showed or had the exact same claim for the US. At least a little bit of supporting evidence that's starting to gather.
This is out. This has been published.
I was asked to review it. I think it was.
Right.
But
So
you
you
reviewed
reviewed
it, but
is this out?
no.
Oh,
no,
okay.
I think the other, I think the other one
You're
actually.
going to be slow on one thing and quick on another thing.
I think there will be a first, but this is double big of a year. So they can be first.
Right. But consistent results then.
Pretty much the claim that you will have an intensification that's mainly driven by increases in the evapotranspiration rather than decreases in the.
Maybe. Are you cutting me off?
I'm not cutting you off because we benefit most from our externals. So if you have another one or two,
Okay, just
Go ahead.
I can stop. It's fine.
go ahead.
I mean, just a final. I had some questions on the final chapter, but maybe I'll just ask you a final kind of general question about what are you doing next?
I think that's the question many of my friends have been asking me. I still have no really good answer, but I think at least for the really short-term future, I feel like I can stay here. So then, of course, I need to discuss it with Sonia. What is our next research project?
Yeah.
But I think like my main idea of what I would like to do is still exploiting a lot of information we can do from steel reconstruction in terms of observed changes in the evapotranspiration. I think you can try to link this, as I said, to, for example, detection and attribution changes. I try to bring it a bit more to the impact side and identify in, for example, links to carbon and try to attribute changes with jobs and carbon sources. So still pretty not clear in my head, as you can probably tell by now. But I think that will be one line of research I would like to go down. And then I think another second very, very important question when looking at evapotranspiration is how much is evaporation? If you know more the drivers and how much is actually transpiration. This is like an all-time question. It's still quite open. Yeah, that's a good question. And then I think there's the new isotope data here that looks promising. So also probably have a look at that and try to disentangle a bit more the contribution of each of these two things.
Okay, that's a good question.
Yeah.
Okay. All right. Thanks.
Thank you. Luca, Sonia, who's
Okay. Then, yeah, also from my side, thanks for really nice presentation. Also, it's been a pleasure working with you the last couple of years. I just wondered about like a technicality. So you show these probabilities for models being included in constraint ensemble, but you never explained how you got to these probabilities and what they represent.
Yeah, so I can, if one of the slides will help, or maybe try without a slide first. So yeah, I think the idea was that in this case, a lot of the studies just compare, for example, observations with models. So one of the things that we wanted to test here was actually evaluate the whole ensemble, capture the distributions. And I think you also know this, but then we looked at the measures like the CRPS, the community run probability score. And then the idea there is that also in the Sigma 5 ensemble, just by the names of the models, we know already that there's quite a lot of overlap. So probably a lot of models that could be similar. So in most cases, including a lot of them, doesn't really help the agreement. So that was why one of the reasons we see a lot of values going to zero, because it's sufficient to include one model and not the rest. And then you wanted to discuss a bit more the MC approach, not necessarily. So yeah, so the idea was pretty much like an iterative approach we did, and I think we discussed it a lot too, on how to address the problem. And then I think there's similar studies that we can do. We are doing similar stuff also in our floor, and then perhaps one of the interesting points there is also that we not only, coming back to the beginning of the question, we weren't only looking at differences between models and observations, but the importance of the metric we used was trying to also quantify differences across models and then to capture the actual spread.
Justin already asked so many good questions, but When rereading your thesis, you start out with this study looking at kind of controls on long-term mean partitioning of precipitation, and you identify a bunch of controls that appear in the context of your work to be more relevant than others. Like, to what kind of implications would this have for versus model development, and then consequently also for like some of the results of your latter studies?
Yeah, so I think that's also probably one of the periods of PhD where it took a bit long. So the idea of the second study after we finished the literature review, if you remember, we started looking at how are these relations we found represented in the models. So then we also have quite a few figures that didn't make it to the thesis or didn't make it to any paper, but we saw that there's quite a lot of differences. So if you look across the spread of single five ensemble, for example, relations of correlations with just the omega you would estimate in the model, and forest cover in a grid cell. In some models was up to 0.8, 0.9. So very, very strongly correlated. Other models basically no relation of these two variables. So I think it's quite a substantial amount of information we can use, at least to try to test, as I said, and evaluate the models in this sense. Of course, in the end, we didn't make it a paper. We didn't make it in the end because we wanted to, and the idea of Crescendo to do an observational constraint study, and then there was no clearly constraint from this. So there's lots of uncertainty in the model, but it wasn't really helping to constrain the future prediction. So I think it's definitely something to look at.
So you think that this might be an approach that could be used to diagnose between model differences and how to identify processes that can possibly be improved? Then like going to your nocturnal water loss study, like you find that it's on average approximately 6% of total evapotranspiration locations where you have observations. Should we care at all about this quantity?
Depends for what. Yes, if you look at full water balance, then maybe could be right if it's 6%. Especially if you're looking at a large scale, then especially considering uncertainties you have in the other variables, you have a large uncertainty about precipitation, then plus minus 6% probably also doesn't play too much of a role there. But on the other hand, maybe we didn't phrase it the right way here, but also one of the motivations for doing that study was there's quite a bit of literature from more the plant physiology community who claims that nocturnal transpiration is like 25% of total evapotranspiration. So a couple of big papers, and then it's like, okay, let's wait a minute again, let's check that in the data, see how relevant it is. Of course, but then not only that magnitude doesn't play a role, but still, if you think, for example, there were a couple of papers already that came out looking at the influence, for example, during last year's drought. In one of the papers, they were trying to quantify nocturnal water loss during the summer or condensation during the summer. And in this particular case is then the 6% of it, when it happens in the year, at what time can play an important role. And then if you link it again back to the models, then if you have more or less water loss during the night, this could also be important for the evolution of the boundary layer the next morning, timing of precipitation the next day. So not only the whole magnitude, but like when it happens, plus I think the scale is relevant.
So maybe as a final question, in both your process studies, it seems like you're having the tendency of looking at process or controls that have been proposed by some other people to be important or highly relevant, and then you are debunking them. Like
You can make a career out of that.
like irrespective of whether it's like your work or not your work, but like do you have like an opinion or view on like how this relates like to an overall scientific process and trying to advance our understanding of how things work?
Yeah, I think, of course, like the first study, especially, like, it's largely based on just a literature review, seeing what was out there that has been proposed. I think with the mountain talks, it's still a small community. Of course, I got interested through conferences. Also had my own ideas from before, like from the field, as I said, that it's starting to grow. So, but then in terms of importance of factors, I would say don't have a claim directly what could be a very relevant control right away, but I think that the thing we should really be investing resources and trying to understand better is higher temporal and spatial resolution, especially Doppler conspiration. I think most of the other variables of the hydraulic cycle we measured, at least have a bit of a longer history in measuring. Doppler conspiration, of course, more difficult, because we don't even see it. That's why I also thought Peru was more important than the But I would say that would be probably the path to go. And then, yeah, right now, at least I can't come up with one, but I also like the idea of exploring. So consider myself a bit more of an explorer. So give me the data, and then also I will try to explore as much of it as try to have like a previous hypothesis, at least right now, on what we can.
Yeah, so also congratulations on your thesis and your presentation. It was also a pleasure to work with you. And there are a lot of open questions, so ideas also for the future. And you have reached many important results. I was wondering from your perspective, what is your most important result?
Today. Well, it's a pretty good question, I would say. Probably a bit more on the later two studies are probably having more direct consequences or more direct impact for the general public, also in the scientific community. I think the idea of future projections is probably something that's much more relevant now for our kinds of decisions. And then having the constraint, as I say, this could be very relevant for team 6, for developing new models, seeing how much we can use in certainty there. And compared to the distribution study, it's a hard balance. I'm not feeling really comfortable to make a choice right now between two. I think I'll be between those two.
Yeah, it was an open question. There was no good answer. So actually, you just mentioned this again. So basically, when you get look at observations, you use some as constraints for models. And also somewhere in your thesis, you were writing actually the outlook that observation should guide the development of models. Obviously, models that you found that not perfect in terms of issues. So I mean, there also in terms of model development, what do you put most emphasis? I mean, you look at those natural fluxes, you look at the issues with ends. Where do you see the most urgent need for work?
Where you put more emphasis in the models. I think one of probably the important questions is not exactly the variable, but still more the time resolution. I think that's probably very difficult, but I think it will be interesting, especially for time models. If you have output and like on journal temporal and journal time resolution, then this could try to explain a lot of the biases, especially with time and precipitation. I said like these biases in mountain fluxes. This could also be very relevant to try to represent better other impacts, future projections of droughts, flooding, and stuff. If you capture more of this smaller temporal variability in the model, I think will be a lot of the work that the people in the group. I think that could be one of the basic tackle to then through that probably indirectly also constrain a bit the projection in the model.
So when I was reading your thesis again, I was looking at this study, the chapter 5, and the fact that the constraint ensemble for most regions, basically the constraint ensemble just produces extremes. Yeah? And there is not much of an impact on the mean, but there is one exception, and that's the
important region.
And so it's actually not an important region in general, and I guess also for you. So I mean, basically the constraint models are much higher. And do you understand this? And do you have any hypothesis for why this?
So the driver behind is again, maybe it's, you can see if we look at, might come with a bit of a surprise. So you want to I think one of the ideas here is that, well, at least we do have a correlation between the model and the projection there. So that already, when the correlation is negative, so if we take correct the problem, then it will mean that models that are wetter in the present are able to dry much more. And apparently, the issue will be that there's, so then if this happens, means that models that agree better with observations are the models that are wetter in the present here. So maybe there's already present day two dry biases in Amazon precipitation. That's why the future ensemble was showing less dry, but couldn't dry up to, at least with the extreme. Yeah. I mean, like in the present. So this, for the correlation, if the model in the present is already too dry, then the change will be less dry. So then it wouldn't decrease too much.
Yeah, so that was actually the change in T minus P, and so your constraint ensemble is more, but yeah.
Yeah, the data will become even drier, yeah.
Yeah, it becomes even drier.
Yeah.
So,
At least for the delta. But you start from a wetter state.
yeah.
But still,
Yeah,
still,
so it's better now, but they're getting better. Yeah.
still, I think, but I think it's definitely something worth looking at. On the other hand, in this case, it might be worth, especially for these more regional studies, to change a bit the method. I think that's something we talked about, and maybe it's worth doing now. So, how we did the constraint was on the agreement of the ensemble, having one ensemble for the whole globe. So then it could be more interesting to see actually which models agree best on this particular region. So we did one ensemble for the whole globe, of course, putting a bit higher weight in the regions where we have higher correlations, and also in the regions with larger areas, of course. But I think, yeah, if we really want to answer more specific questions, it's probably worth trying to analyze, especially if we trust our physically based relations that we think that models, if we start with, they can dry more because they have more water available. So if we agree that this is a brilliant process that should be captured in the projections, then it's probably worth repeating the analysis and using or recomputing the probabilities of the models to be in the constraint ensemble, just using data from
Yeah, so I mean, it has important implications. So as you were saying, the models would be then weather at the time that, but could you use acid constraints now to assess whether those models are really doing well? I mean, whether they really make sense? What would you be looking for?
Like, well, of course, we need to see like relationships with the future to decide if we're really focusing on constraining uncertainty. What we would need first of all would be that there's a correlation between a state we can observe in the present and the recent past and the future change. This would be the first thing that we need to find. And then things to look at is now we have the reconstruction. If we have these local transpiration estimates that observation based, we can also probably use them to improve this. But in this case, the study was done before Jonathan Vincent came up with the reconstruction products. I think including that for the constraint could be quite useful.
And so, yeah, also follow up on this. So, I mean, in your constraint ensemble, as you were showing, in the end, you have very few models. So,
we have to find,
yeah, and so I was wondering, I don't know if you had the curiosity to check how those models were matching, for instance, your constraint of omega values from the study, or I mean, do you trust those models? Did you check for everything with those models that could tell you those models are really good, or you don't?
I didn't check the omega values. I would say that that's another point, of course. I think everybody has their own favorite model. It seems to be in the case of the modern community. Things you could think of here is that, of course, some models can be better in present day precipitation, but not necessarily better in capturing some other processes. So then there could be differences in that. Although I think there was, a few years back, I cannot remember who did the study, but someone was showing that most of the observational constraints, the models that are being chosen, actually agree across a lot of metrics. I think it was maybe, and then they have special metrics for precipitation, temperature, and always the same models that were being were ending up. So then I think that would be useful. I think one of the very first steps that will see how bad this constraint is to reapply it to single state. And then see if we have more models, and then think we can use that.
I mean,
argument.
yeah. It also for like these nocturnal order factors, you need to get semi-prime models.
Yeah, then
Remember if those models were doing okay, if they were outliers?
that we can definitely see. So we can check is KNSM, the hydrogen pretty much, and DSM are the good models. Right? I think they have the internal water. There in here you have just a ranking. You see if they're very outliers. So if you look at KNSM didn't have 3-hour data, but I think was one of the good ones, which is good. This is the ranking, so these ones are a little bit lower. So here the average will be good. So this is the overall ranking of the distribution of the models. So this model is in the lower end of nocturnal water loss. These models are always overestimating nocturnal water loss relative to the other models. So according to observations, the actual value will be a little bit lower. So then models that are a little bit in the lower side will be a bit better. Hydrogen is the lower side. GMT is in the lower side, which was kind of the good one for before. So at least there's some, at least there's a bit of an agreement. Yeah.
It says at least 1 hour.
No, honestly, I'm done. Just in as a last question.
Yeah.
Really?
You said you had one more.
I've actually seen quite a few studies where they've looked at evaluating climate models over a whole range of different metrics, not just precip and temperature, but also drought and things to do with extremes and variability. From those studies, I've seen it's all over the place. So you don't get this clustering of good models that perform, well on most of the metrics. It seems to be pretty random. So I think it's worth looking at in a bit more detail. But I think you would see that performance on multiple metrics if those metrics are connected, of course.
Yeah.
But if they're not connected in a reasonable way, because of timescale differences or whatever, then there's no reason I don't think we should see similar performance.
Yeah. If you have a particular question, just to comment on your comment. You can comment.
You can just say,
Yes, you can comment on your comment.
if you want to.
I agree. I think one of the last things that we're discussing now, and one of the last discussions was maybe it's worth trying to come up with constraining metrics that are normalized by climate sensitivity. That's also something I haven't fully processed, but to try to balance a bit more like this idea. It's probably not a fair comparison if you have different states in the model.
Okay. Last chance for a question from the committee, if there's one. Not the case. In that case, it's up to the general audience, and the general audience is here in the room, but the general audience also, we have an outpost in Ecuador, right? So,
I don't know if you're watching, but
if they want to ask a question, they should also go ahead. All right. Is there questions from your side? Go ahead.
Well, thanks, very nice presentation. As I guess you know, I'm really interested in this work. I think it's great, especially towards the end. And so I have some sort of more technical, small scale questions, I guess. And I was just wondering, like, after your comment saying that you end up with only like 6 or so models in the constraining, what is the probability that you reduce your spread just because you take 6 out of 30 models? Is that part of the Monte Carlo exercise? I mean, what is the probability that your spread stays almost the same if you 5 and 95% odds by picking only 6 more or less out of many models? Isn't that sort of almost a little bit built in? But I guess you see regions where that's not the case. But I was wondering, what is the probability?
well, also Janssen, you will end up constraining. Of course, by default, you will end up constraining. But I think one of the nice things of the approach is that you don't discard a model directly. So there's always a probability still there. And that's why I pose it more in terms of the probability ratio. Because actually, if you look at the pool spread of both the constraint and the pool ensemble, then in most cases, the pool spread is the same result. Because no single model is completely kicked out. Just like the probability decrease is very, very low, so then it's out of the top 5% that I chose for the experience. Of course, there's by default, you'll have initial sample size. We try to account this by not only having 5 models and then saying, okay, that's our spread, but just by recomputing an ensemble of the fixed size, like 100 models, based on the probability. We just have those probabilities, sample random from those probabilities, and then have a sample size of 100, and then get the spread. But I think pretty much then, if the probabilities are that different, then we can just do those quite small.
In the Amazon, could it be that the CO2 effect is not something you can constrain, I guess?
Precipitation.
And I feel like some of these models have pretty strong response to CO2 in their rapid temperature, whether it's realistic or not.
Yeah.
So how does that factor into your constraint? I mean, it doesn't, but like, how would you interpret your constraint?
Probably think a bit more about that, just on the top of my head, but that would mean that the change is stronger. It probably doesn't really show in the correlation, but it will mean that if you think that models are overestimating the change in the rapid transpiration, then you will have a stronger decrease of these particular models, making it drier. So the overall link there, if this is the case, will be that models that are, whether in the present in the Amazon, are those models that have an overestimation of the rapid transpiration due to CO2 effect in the future. So it could be something very interesting to look at. So if we think this is the causal link, we know which models are the ones that are wetter in the present. We should go and check on those models, how do they behave for the future rapid transpiration, see if they're actually overestimated. Thanks, very good idea.
Any other questions? What did you do with groundwater?
Not much.
Not important.
No, so like we use it on.
So you is the one.
Yeah, so for it depends on the cases. So like in the first. So I think in the first study we were looking at very year mean, also long-term mean, that's like the whole conceptual scheme of the Silica framework. So then at those time scales, you assume that there's a balance and there's hardly any change in storage, so you can neglect it in the water balance. So then any precipitation will be already evaporated or turned into runoff. Of course, the changes in storage will be much more relevant at seasonal time scales or even a year to year, but if you take the long-term mean, the assumption generally that there's not so much of it. And then where we do use quite a bit of groundwater is for the assumption of the sort of changes in the dry season. And then I don't use it directly, but it's based on the reconstruction of terrestrial water storage. So the reconstructions are pretty much the whole water column. So you have covered surface in the plant, below ground, deep aquifers, everything included there.
Unless there is a last other question, I would like you and Ecuador to leave the room and we give again a big applause.
Desconectándonos aquí.